Hello everyone. In this video, we talk about classification in machine learning. And in particular, we start with the problem of binary classification. In this case, we have two possible outcomes or labels, and we can represent these using 0 or 1, where 0 is one class, 1 is the other class. As mentioned in previous videos, in this case, 0 and 1, they do not have any numerical value, and they're simply two different numbers that we use to distinguish between data points that belong to one class versus the other one. Therefore, it is common, depending on the context or textbook, that sometimes these two classes are labeled as -1 and 1, or positive and negative. For example, in the version that we have here, 1 can be considered as the positive class, and 0 you can think of that as the negative class. Among classification algorithms, we mainly focus on logistic regression for this notebook. And because it's one of the most widely used classification algorithms, and it's a direct generalization of linear regression that we just had. However, there are some clear differences between linear and logistic regression, in a sense that in linear regression, we are trying to predict a continuous label, but in this case, we are trying to predict a discrete label, right? So this is, either 0 or 1. And also, as we're going to talk about in this lecture, loss functions that we use for classification problems are typically very different than their regression counterparts. To get us started and define logistic regression involves a probabilistic model of the form Py given x and theta. So this is what is known as conditional probability, meaning that we want to find the probability that the data point belongs to one of these two classes given the input, right? So remember in the lecture or 12, we had the example where we wanted to predict bank loan default based on income and debt. So in that case, income and debt, there were two features that they were given as inputs. And so that's what we have here for X. And Y in that case was whether an applicant will default or not. So it's either 0 or 1. And theta here is very much similar to the theta we use for linear regression. It is used to represent the unknown model parameters. So in order to understand logistic regression, we need to recall the probability mass function of the Bernoulli distribution. Just to recap, Bernoulli distribution is a random variable which is discrete and has two possible outcomes, 1 and 0. This is something we can use, for example, to model the outcome of a coin flip, right? So in this case, we get either heads or tails, and we can call this like 1 and 0. And Bernoulli distribution is very simple and useful because it has only one parameter theta, which tells us the probability that y equals 1. And obviously, because we have a binary case, then we also find the probability that y equals 0. So in this case, the probability that y equals 1 is theta, which is the parameter of the Bernoulli distribution. And since the sum of probabilities must equal 1, the probability for y equals 0 is 1 minus theta. And in fact, we can write this in a very compact form. As you have seen, this is something that we always want to do in machine learning and data science, to write functions in very compact forms. And we can write this in this form of theta raised to the y, 1 minus theta raised to the power of 1 minus y. So in this case, you can see that if y equals 1, right, because y can only take two values, 1 or 0. If y takes the value of 1, then we get theta. And here, because we have 1 minus y, we get 0, and any number raised to the power of 0 is 1. So this whole thing is theta. And if y equals 0, then we get 1 minus 0 here, and we get 1 minus theta. So that's why you can write this step function here, or say this piecewise function here in this compact form. And therefore, the model that we use for logistic regression is based off of this Bernoulli distribution. We say that the probability that the output y given x and theta is this Bernoulli distribution, where the theta, or the probability that we need to define the Bernoulli distribution, is coming from this function of the input applied to the sigmoid or logistic function. So that's why we call this method logistic regression. So we have to explain a couple of things here. The first thing is the sigmoid or logistic function, to define this and understand why we have to use this. Here we have the mathematical expression for logistic function, which is 1 over 1 plus e to the negative a, or as we have written here, exponential of negative a. So we can use mathematical tools to find the limits of this function and horizontal asymptotes and things that we have, we see a lot in calculus. But again, this is more a programming course, so we want to use tools such as NumPy and Matplotlib to be able to visualize this function. And therefore, we import NumPy as NP, we import Matplotlib. Also, we select a range of a values from -10 to 10. And here is where we define this sigmoid logistic function, which is 1 over 1 plus e to the negative a. And then we plot a and the values that we get from this sigmoid function. So if you run this cell, you can see the shape of the sigmoid or logistic function. So here we have restricted the x-axis, or here we call it a, to be between -10 and 10. This, in fact, can be from -infinity to infinity. But the most important thing is the shape of this function. And one thing that we have to pay attention to is that the range of this function, and the range is the set of values that this function can take, as you can see here, is from 0 to 1. So this is why we need the sigmoid or logistic function for classification purposes. Because if you look at what we have here, this sigmoid or logistic function acts as the probability parameter for the Bernoulli distribution. And we know that the probability of a random variable is always between 0 and 1. So if we do not use this sigmoid or logistic function, we can end up with a value of this function f, which is outside the acceptable range of 0 to 1. Therefore, in this model, we assume that we can have any function of x parameterized by this theta. But after we find this function, we have to pass this through this sigmoid or logistic function. And this sigmoid or logistic function, if you look at the y-axis, is always from 0 to 1, which means that now we get a valid probability score. So that's one very important piece here. Now you may wonder, well, why should we use, this sigmoid or logistic function? There might be other options as well. So here it gets a little bit technical, but I wanted to include this information here, that the sigmoid or logistic function has a very nice property in the sense that once you find its derivative, so you see that this is the function that we have, we can write it as 1 plus e to the negative a raised to the power of -1. Once you take its derivative with respect to its input, which is a, and you simplify this, you can actually see that the derivative can be written as the sigmoid function times 1 minus the sigmoid function at that point a. So this is a very useful property because this function has a very nice closed form derivative. And in practice, yes, you may be able to define different functions that they have the same range, meaning that the output is always from 0 to 1, but then those functions may not have such a nice property. And since we need to find gradients and derivatives that we talked before, this means that this can be extremely helpful to have this knowledge. So in this cell, again, we want to use programming here mainly rather than going through math in a very comprehensive way to get a sense of these results. So in this case, we're going to plot the sigmoid function and also its derivative, which is sigmoid times 1 minus sigmoid, as we just have here. So you can see that here we get the derivative plotted in red, and this makes sense because where we are, for example, at 10, you can see that the slope of tangent line is, almost 0, and that's what is shown here. And the same thing with negative 10, and you can see that the max derivative or the slope of the tangent line is actually at 0, which is 0.25. Okay, so now we know that this is the sigmoid function, this is its derivative, and its derivative has a very nice format. So what does this mean in terms of binary classification, which is the main topic of this video? So you can see that now we can actually find these probabilities of the data belongs to class 1 and the data belongs to class 0. So the probability that data belongs to class 1 is the sigmoid of A, right? That's the parameter of the Bernoulli distribution, which is 1 over 1 plus e to the negative A. If you want, we can multiply both numerator and denominator by e to the A to simplify this, and that's what the result that you get. And remember, since these two events, y equals 1 and y equals 0, are the two only possible cases, the sum of probabilities must equal 1, which means that the probability of y equals 0 is 1 minus the probability of y equals 1, which is sigmoid of A. And you can simplify this based on subtracting this value from 1, and that's what you get. And similarly, you can multiply this by e to the a for both numerator and denominator. Something also important to keep in mind here is that if you divide this probability of y equals 1 by probability of y equals 0, they have the same denominator, as you can see here. So this means that these two terms will cancel, and you just end up with e to the a. And now if you take the log of this, now you just get what you pass through the sigmoid function. So what does this mean? So this means that if you want to find the inverse of the sigmoid function, which is called the logit function, you need to find log of p over 1 minus p, right? Because p is the probability that y equals 1, and the probability that y equals 0 is 1 minus p. And this is what is known as the logit function, which is the inverse of the sigmoid function. Since these functions are very useful and popular in machine learning, you can see that they're actually already implemented and they're part of the SciPy package or library. And inside that, there's a module called special, and we have these two functions. So this exp that refers to the logistic function, and logit obviously is the logit function that we have. So these two are inverse functions. And we can actually plot them, right? So here we use subplots that we learn when talking about matplotlib. We create a 1/2 grid, and you can see that in one case we are plotting this logistic function, and then in the second plot the logit function. And if you run this, you see the familiar logistic function and then the logit function. And you can easily interpret this, right? So you know that if you pass 0 to the logistic function, then you get probability 0.5. And the same way, you expect that if you want to find the inverse function, if you provide 0.5 to this logit function, then you get 0, right? So this means that the logistic function is a very nice function because it has closed form derivatives. It has an inverse function. So if you want to know what input to the logistic function will give you 0.5, you can actually use the logit function and then find this value. So these two together will give you a lot of information. So now we are at the step that we can formally define logistic regression. So remember, in logistic regression, the logistic refers to the logistic function. And the reason that we call this logistic regression, even though it's technically a classification problem, because it does look very much look like linear regression, right? So this function f that we have there is actually assumed to be the dot product between the input vector and the vector of parameters. And so overall, for logistic regression, the probability of y given x and theta comes from a Bernoulli distribution with this parameter sigmoid of theta transpose x. Which means that what we really need to remember and keep in mind is this final formula that we have here, that the probability of y equals 1 given x and theta is the sigmoid or logistic function of the dot product between x and the vector of unknown thetas. And that by definition is 1 over 1 plus e to the negative theta transpose x. And when you find this probability, you also have probability of y equals 0 because that probability is 1 minus this value. Okay. So the next question is how can we find this theta, right? Because that's the whole point of model training or fitting. We need to be able to find unknown parameters. And for that, we need to define a loss function. And in this case, we cannot use the quadratic loss function because, again, these 0 and 1 are just some labels and they do not have any numerical value. So one idea is to use the loss function that we had in lecture 12, which was the misclassification rate, where we use the indicator function that measure whether the true output or the true label is equal to the class label that we predicted. But it turns out solving that problem is not an easy problem. So we need to find a loss function that can be easier to optimize. And the loss function that we mainly use for logistic regression is the one that is provided here. That if the true output is 1, then the value of loss function is negative log of mu n, and mu n is what we get from the logistic function. And if yn equals 0, if the true class is 0, then we get negative log of 1 minus mu n. This is somewhat complicated to figure out why this works just by looking at this equation. But again, in this course, we can use Python for visualizing this loss function and making sense of what it does. In order to do this, we're going to define this loss function, and it's called cross entropy loss function. That's what this CE stands for, which it takes two inputs, y and this mu. And remember, mu is the probability. If y equals 1, then we have to return negative log of mu. And else, which means that if y equals 0, then we have to return negative log of 1 minus mu. And in order to find mu, we're going to create some numbers from negative 10 to 10 and pass them through the sigmoid function or logistic function to find this mu that we have here. And from now, we can just visualize these two loss functions. Let's start by looking at the case where y is equal to 1. So the true label or true output should be 1. So in this case, if you find that the probability that y equals 1 is also 1, that means that you're 100% confident that what you're predicting should be 1, and that matches with the true output, which is 1. And therefore, in this case, the loss or cost of this prediction is 0 because we are not making any mistakes. However, the cool thing about the cross entropy loss function is that as we get this probability closer and closer to 0, which is undesirable because that means that we are making a worse prediction, then the cost for that increases substantially. You see that this is almost going to infinity, right? So that's why this is a very nice model for training classification problems. And the same thing happens with probability with this second case, which is y equals 0, the blue curve. So in this case, something you need to keep in mind is that probability of y equals 1 and probability of y equals 0, they are complementary, meaning that one is 1 minus the other one because the sum of probabilities must equal 1. And therefore, in this case, if probability of y equals 1 is 0, this means that probability of y equals 0 is 1. And the data point that we have belongs to class 0, so there is no penalty to pay. And as we make worse predictions, meaning that now the probability of y equal 0 gets closer to 0 because now you have to use 1 minus this number. Now this value of loss or cost function increases substantially. However, in general, in my opinion, it's just easier to focus on one of these two. For example, y equals 1, the orange curve, because that matches better with what we have here as the label. And here it's very clear that when probability of y equals 1 is 1, and the data point belongs to class 1, there is 0 error. And as you get closer and closer to this probability being 0, then obviously we are making worse predictions and the cost should increase substantially. And this is consistent with what we have here. So you can look at the behavior of these functions as, this mu gets close to 1 or 0. But overall, in this course, we can always plot these functions, and it's much easier to interpret them. Okay, so now in terms of using logistic regression in scikit-learn, the nice thing is that it follows the same path as what we did before. So the very first thing, we need to import the logistic regression class from linear model. It's a linear model because, as you saw here, the assumption that we make is that this function, which is inside the sigmoid function, is a linear function. And we can do this by importing logistic regression from scikit-learn.linear model. And then we need to instantiate this class to create this object, which I call here model, but this can be any name you want. And here there are some parameters that also you can choose from. For example, you can choose the regularization strength, which is an important way of avoiding overfitting that we had in the previous lecture. Also, the exact optimization technique that we want to use. And since the optimization technique here is an iterative process, we can set the maximum number of iterations. So depending on how much you understand the underlying mechanisms of logistic regression, you are more than welcome to adjust them. But if you don't know very much about them, you can use them as is without providing extra parameters. And after that, we use model.fit. So that's the part that we are going to minimize the loss function that we have. This cross entropy loss function average on the training data. And then in the prediction stage, now here is the main difference with this one and regression problems. We have two methods. We can use predict to predict the class label, or predict proba to predict the probability of each class. Because remember, what really logistic regression does is to give you this probability that y equals 1. And this means that you have the right to say that, well, I only assign label 1 to a data point if this probability is above some threshold. So if you don't have any kind of preference, you can put the threshold at 50%, meaning that if it's more than 50%, then I'm going to assign that to class 1. But if for some reason class 1 is a very important class and you want to make sure that you are not misclassifying data points by saying that they belong to class 1 when they don't, then you can increase the threshold for the probability and say that, well, I only assign a data point to class 1 if this probability is above 80 or 90%. So therefore, in scikit-learn, you have the option to find the probability if you want to decide yourself how do you want to assign these data points that you have in this X test to the classes, or just use .predict, and this is by default will use 50% or 0.5 as the threshold. And similar to regression problems, we also have to evaluate this model using some metrics. And here we have several metrics such as accuracy, precision, and recall that I'm going to explain them in the next slide. So in order to evaluate classification models, especially in the case of binary problems, it is very common to form something called a confusion matrix. So this confusion matrix, as you can see, the rows are the true labels. So these are the labels that we are given in the data set that we have. And the columns are predicted labels. And here we use the more conventional notion of positive and negative classes. So instead of 0 and 1, we call this -1 and 1. And therefore, if a data point really belongs to the negative class or the 0 class, and it is predicted to be negative or 0, then that's considered a true negative. And the same thing with true positive, right? If a data point belongs to the positive class and it is predicted to be positive, that's true positive. And now the misclassifications happen in these off-diagonal terms. If a data point is supposed to be negative and predicted to be positive, that's a false positive. And similarly, if a data point was supposed to be in the positive class and now it's in the negative class, that's a false negative. And based on this, now you can define various metrics. So what is accuracy? So accuracy is the total number of correct predictions divided by the total number of predictions. So this means that it's true negative plus true positive over true negative, true plus true positive plus false positive plus false negative, right? So that's the ratio of correct predictions. But then we can also define these more appropriate metrics depending on the application, where we look at precision, which is false positive over false positive, precision, which is true positive over true positive plus false positive. That's the equation that we have here. And what this tells us is that among the data points that are predicted to be positive, how many of them are actually positive, right? So it looks at this column that we have here. Or in other words, it's really trying to look at the number of false positives. On the other hand, we have something called recall. And recall is what we have in this row. So it's true positive over true positive plus false negative. And this tells us among the data points that are actually positive, how many of them are correctly classified. That's what is also called true positive rate. And in some domains, for example, medical domains, this is what is mainly referred to as sensitivity. And again, in medical domains, also they like to define something called a specificity, which is the true negative rate. So this means that among the samples that are actually negative, how many of them are predicted to be negative? So it's true negative over true negative plus false positive. And this is what is known as the true negative rate. So I would definitely recommend you to have this picture in mind, because that really is going to be helpful to figure out what precision, recall, and other metrics are. So that really is helpful. But let's see how this works when we are using scikit-learn. So in this case, we're going to use that iris flower data set that we have used before. And now if you look at here, you can see that this data set, which is part of scikit-learn, has multiple portions. So we have data, target, and the data means that that's the X metrics, target is the Y vector. Also, we have the target names, feature names, etc. So just to show this is what we have in iris data, right? So this is just the data or features part. So we have the sepal length, width, petal length, and petal width. And in this case, we have 150 data points, and each one has 4 columns of features. Then we can look at where we store the outputs or the class labels, and especially we can use value counts. You can see that this is a very well-balanced data set in a sense that we have 50 data points with class label 0, 50 with class label 1, and 50 with class label 2. So this one is actually 3 classes, but you're going to see that we can convert this to a binary classification problem. So these are the target names, the names of 3 species of the iris flower. And the way that we convert this to a binary classification problem is by checking to see whether the flower belongs to this Virginica species or not, right? So once you use this, right, so this is either true or false, which means that now you have a binary classification problem. You want to predict whether the species of these flowers is one of these 2, Setosa or Versicolor, or this Virginica. And in this case, we are only working with one of the input features first, because that makes it a little bit easier to visualize this classifier, and that's the petal width. Obviously, we have more features here, but that's the only one that we want to consider at this point. And as we said, we always use train test split. And in this case, we can instantiate this logistic regression and do model fitting. So this means that now we're going to find parameters that minimize the loss function. Okay, so now we're going to create some test data points. That's what we call it, this, X new. And these are some numbers from 0 to 3 that we use linear space. And in this case, I want to mainly show you the probabilities. So that's why I'm using predict underscore proba. And if I run this cell right now, so you can see the main idea here, right? So we have this petal width on the x-axis. So this has values from 0 to 3. And then the probability, what we get from this predict proba, is on the y-axis. And we know that probability is always from 0 to 1. So this means that the probability that the flower belongs to this class, this Virginica, it increases as the petal width increases, right? So for example, when petal width is 3, we are almost 100% sure that that flower belongs to the Virginica class. And we have also the other way too, right? So as the petal width decreases, this probability gets closer and closer to 0. As we said earlier, what you can do, you can always put the threshold at 0.5 or 50%. So this means that anytime that the petal width is greater than what number that we have here, then we assign that to the Virginica class. And if not, we're gonna assign that to the other class, because then the probability that you see through this blue curve is greater than 50. And remember, because the sum of these two probabilities must equal 1, that's why they have like this kind of like opposite behavior, right? So in this case, you can see that once one increases, the other one should, decrease. And to show these probabilities for some of these test data points, I'm using this predict proba. And this tells us for the first test data point, the probability that it belongs to class 0 is 0.84, almost, or 85. And the probability that it belongs to the other class is 0.15. So the sum of these two must equal 1. That's the principle of probability. And you can see that now for the test data point, the second one, the probability that belongs to class 0 is 0.99. We are very confident. And then the probability that belongs to the other class is now almost 0. And you can see that now we have like kind of like the opposite behavior for the third data point. So this means that this X test goes through the linear transformation, goes through the sigmoidal logistic function, and it gives us these probabilities. And if instead of predict proba, we use predict, now we lose all this probability information and we just get some labels, right? So in this case, class 0 is false, class 1 is true. So if we have to assign this to one class, then it definitely belongs to this first class, which is class false, which means that it's not the Virginica species. And the same thing for this one, for the second data point, but for the third test data point, that definitely belongs to the class that we have in mind. So that's true. So therefore, if we want to change this rule, we can always look at predict proba and say that, well, I'm going to assign this, let's say, to the false class, not only if I get at least 50 or 60, but maybe at least 70%, right? So that kind of like changes the way that we assign labels to these data points. So here we have some homework problems to practice more with this iris flower data set. And you're going to use the train test split from model selection with this split ratio. And now you want to evaluate the model using the metrics that we discussed, such as accuracy, precision, and recall. Because in this example that we just had here, we really didn't officially or formally evaluate the model. We just wanted to interpret these probabilities that are assigned to these data points. But in this case, you work with these predicted labels, and you're going to convert them with the true labels using these confusion metrics. And remember that all these precision, recall, they are implemented in scikit-learn, and we know that they are part of the scikit-learn.metrics module. We're also going to work with this Wisconsin data set. This is a very also interesting data set that you can use for training classification models, and we follow the same procedures. We're going to use logistic-regression model to predict classes for testing data points and then evaluating the model. And in the last problems, we want to work with these probability thresholds that we just mentioned, right? What happens if we use 0.5, which is the common value to assign data points to classes, to 0.6, 0.7, 0.9, these different values. And in this case, you have to use first the predict proba method to get these probabilities, and then based on those, you can assign labels to data points. Thanks for watching.